Okay, 1.5. Okay, laws of propositional logic. Okay. Okay, the first law is the idempotent laws. Okay, and that is if I take P and P, that's logically equivalent to P. Okay, if I do a conjunction on P, I get P. Okay, also, if I take P or P, I should get a conjunction, or sorry, disjunction on P. I should get that to be logically equivalent to P. Okay, okay, the associative laws. Okay, of P, sorry, or Q in parentheses or R is logically equivalent to P or Q or R, Q or R in parentheses. Okay, so it doesn't matter. As long as we're doing all or statements, we can group them in any order or in any way. Okay. Not in any order, but in it, we can group them first and second however we want, as long as they maintain the order and they're all or statements. Okay, the same thing with and statements. If they're all and statements, we can group them in any way, as long as they're the same order. Okay, and they're all and statements. Okay, very similar to the associative laws of addition, okay, in mathematics. Okay, the commutative laws. Okay, tell me that if I have P or Q, that's logically equivalent to Q or P. Also, P and Q is logically equivalent to Q and P. Okay. Okay, the distributive laws. Okay, is P or Q and R is logically equivalent to P or Q and P or R. Okay, at the same time, P and Q or R is logically equivalent to P and Q or P and R. Okay. The identity laws is that if I take P and I do a false statement, if I do P or a false statement, that will always just produce P. Okay, P or a false statement, it will always just produce back P. Okay, likewise, if I take P and I do an and with a true statement, that will also always produce back logically equivalent to P. Okay. Okay, domination laws is P and false will always get me out a false statement. Doesn't matter what P is. And P or true will always produce a true statement. Doesn't matter what P was. So it just tells me that when it's an and, false dominates, and when it's a when it's an or, true dominates. Okay, double negation laws. Or I should just say law. Double negation law is if I double negate P, that's the same as P. Okay, not P is just P. Okay, the complement law okay, if I take P and not P, what will that always produce? P and not P. What will P and not P? If P is true, not P is false, right? If P is true, not P would be false. Put those together, I get false. If I take P is false, then not P is true, put those together, it's still false. So either way, it's false. Okay, if I take P or not P, one of those always has to be false and one of them always has to be true, but a true with an or statement is always true, right? Thank you, Anthony. Okay. Okay, we've already seen this one, but we're going to write it again because we need to memorize this. De Morgan's laws okay, not P or Q is logically equivalent to not P and not Q. Okay, not P oops, and Q is logically equivalent to not P or not Q. Okay, absorption laws. Okay, P or P and Q will always be equal to P. Okay. Okay, so Q gets absorbed. Okay, likewise. Okay, P and P or Q is also equal to P, is logically equivalent to P. Okay, conditional identities. Conditional identities. Okay, and these are super helpful. Okay, is that we have P goes to Q is logically equivalent to not P or Q. Okay, so we have a conditional identity that we can actually write in terms of a propositional statement. We have a conditional statement and we can translate that into a propositional statement. Okay. The same with P if and only if Q is logically equivalent to P going to Q, okay, and P or Q going to P, okay, okay, which we could use, if we really wanted to, we could use the statement right above it to turn that all into one statement that doesn't involve any conditions. We could say that this is not P or Q, and, okay, not Q or P. Okay. Kind of cool. Okay, let's prove the first one here. Let's show that this is true. Okay, if we do a truth table on this conditional identity, we go P, Q, we would need not P, we would need P goes to Q, and we would need not P or Q. Okay, let's prove this one to be true. Okay, that they are logically equivalent. We want to know, are these logically equivalent? Okay, so T, T, F, F, T, F, T, F. Okay, not P is going to be F, F, T, T is going to be F, T, F, T. Nope. Sorry. Yeah, F, T, F. Oh, no. We don't need not Q. My bad. It was, sorry, I was going too fast. We only need P goes to Q. Okay, so what is P goes to Q? If it's true, it's true. If it goes true to false, it's false. If it goes false to true, it's true. And if it goes false to true, it's true. Okay, what about not P? Not P is false with Q. Okay, so false or true is true. False or false is false. True or false. Okay, I'm sorry, true with true is true, and true or false, true or true is true, and true or false is true. So they are logically equivalent. Okay, example 1. Okay, prove the proposition P goes to Q, and it's contrapositive not Q goes to not P are logically equivalent. Okay. Okay. Prove this to be true. Okay, using some of these identities. So we're not going to use a truth table here. We're going to actually go through a formal proof of this. So we're going to say P goes to Q is logically equivalent of not P or not Q and not P. Okay, this is the proposition. Okay, logically equivalent statement. Okay. And then we want to do a proof of this. Okay. For a proof, we need something called statements and then reasons or justifications. Well, I'll make it a little spicier. Justifications. Justifications. Okay, first statement is P goes to Q. Okay, I want to build a logical bridge. Okay. I want to build a bridge. Okay. Okay, from this guy to this guy. Okay, so my first statement is going to be where I'm starting. P goes to Q. Okay, so 1. Okay, okay, P goes to Q. What's the justification? That's just the proposition that I'm starting with. Maybe I'll call it initial proposition. Or initial conditional statement, however you want to say it. Okay. Okay, number 2. Okay, where can we go from here? Well, let's use some of these laws that we just went over. Well, and the one that we just proved. The one that we just proved was this one highlighted here. That P goes to Q is the same, logically equivalent as not P and or Q. So let's use that one that we just proved as our second statement. So P, or sorry, not P or Q. Okay, and this is a conditional identity. Right? Okay, number 3. Okay, again, I'd like to go get not P's and not Q's. Okay, so how can I get a not Q? Well, I could not the Q. So I'm going to go not P or not Q. And what law is that I use there?
Double negation.
Yeah, thank you, Lukesh. Okay, it's double negation. Okay, double negation law. Okay, number 4. Okay, I would like to get the Q on the other side and the P on the other side. So I want to swap sides. So how can I swap sides here? Well, I can do the double negation of Q or double or single negation of P, and that's the commutative law. Okay, and then, okay, 5, this is going to become the negation of Q goes to the negation of P, which is just my conditional identity in reverse. Okay, it's just my conditional identity in reverse. It just says, hey, you know, if you've got this thing, okay, a negative of P or Q would go to P goes to Q, right? It's the same thing that we did up here. Right here, we just are doing it now in reverse. Okay, and with P and Q swapped. So Eric asks, can't you just do associativity and then do the conditional again? No. Associativity involves 2 different operators. Oh, commutative. Okay, can you just do commutative and then do, oh, okay, there you go. It's is it necessary to use double negation? Yeah, because there's no way to get this guy without double negation. Does that make sense? No, you won't. You will end up with a Q. If you don't use double negation, right? Oh, can you use commutative? Oh, I see what you're saying. Can you just use commutative without using double negation? Let me think about that for a second. P goes to Q, but the negation has to be the first one. No, you do have to do double negation because you're not going to have a negative. And if you don't have a negative, how can you? if you don't have a negative, then you can't go to the can't make it a conditional. Okay, I mean, I do like the question. He's basically, they're saying, if Q goes to negative P, can't you just write this as negative Q goes to negative P? And the problem is that this works in this direction, but I do not believe it works backwards. Okay. I don't think it works going forwards. Okay. No, that's what we're trying to show, right? Yes. Okay, so the problem is this, right? The conditional identity says this, and I can rewrite it as negative P or Q is logically equivalent to P goes to Q, right? That's the conditional identity that we're working with. Okay. The problem is, once again, the problem is that you're actually double negating it in your mind. You're just not putting it down on paper. You're putting in a negative where there is none to be put in. If I had Q and not P, right? Well, how do I go from this to this? How do I go from that to that? Right? This to this is real simple. It's just the same thing. But how do I go from not P to P? I'm going not P to P. If I don't have a not to go there with, I do need the not Q so that I can take this guy and not Q him, and then take the not P and not P him. Does that make sense? It's good question. So yeah, you have to have a not that will translate that. Yes. Yeah, in a proof, you have to use the rules in the order they're given in a proof. Okay. And so we can write, therefore, it has been showed, it has been demonstrated, it's quod erat demonstrandum, okay, quod erat demonstrandum, which is QED, which is Latin for it has been shown, or it has been proven. Okay, therefore, it has been shown and it has been proven that P goes to Q is logically equivalent to not Q goes to not P. Okay, and then we put a little square there, okay, to show that that's the end of the proof. This little square means QED, which is Latin for quid or quad. It's not quad, it's quod. Sorry, QUOD. Quod erat demonstrandum. Sorry, demonstrandum, which means it has been demonstrated. Okay. Okay, example 2. Okay, simplify the compound proposition okay, here we're just simplifying, we're not actually proving. Okay, so I'm going to simplify the compound proposition. Okay. Okay, not P or Q, or not P, okay, and Q. Okay. So how can we deal with this guy? An idea is on what we would want to do first.
Maybe De Morgan's.
Yeah, De Morgan's on this guy here, right? Okay, so yeah, we want to we want to distribute the negation, so that's De Morgan's law. So that's going to be not P and not Q, or not P and Q. Right? So we used De Morgan's on that one. Okay. Sorry, this should be upside. I wrote that wrong. That should be that way. Okay. So now what do we have? Now we have the distributive property. Okay. On not P. So if we take not P, okay, and we distribute, okay, okay, so we would distribute not P and Q, not Q and Q. Okay. Not Q or Q. Well, what do we say not Q or Q always was?
True.
Now it's always true, right? This thing not Q or Q is always true. Okay, and so this guy was due to distributive law. This guy is always true due to the complement law, right? Okay, a proposition and its complement, when we not something, it's its complement. So that's the complement law. Okay, and so, and not P and true is always going to be what? It's always going to be not P, and that's an identity law. So we could say that this thing simplifies to not P. Okay, if we wanted to make the statement not P or Q and not P and Q, okay, is logically equivalent to not P, I could do that, but I would have to set up a formal proof, okay? This is a simplification, not a proof. Okay, if I wanted to do this, I would need to do a proof, which would list all of my justifications and my reasons. I pretty much have set up the proof already, right? Okay, by doing this, by listing out the reasons, the justification for each step. Okay, we could easily turn this into a proof by just putting the statements and then the justifications, and then making it out to be a formal proof. Okay. Need to use formal proof. To prove logically equivalent. Okay. Okay.